Okay, we stopped here in the last lecture, right? So we'll start from here. Additional notes on BOD. Although 5D BOD has been chosen as the standard value for most of the wastewater analysis and regulatory purposes, ultimate BOD is actually the better indicator of the total strength. I already mentioned those when I try to explain why 5D BOD. So this is one of the example. In this case, I have two waste, right? Two different, this industrial waste, this is municipal solid waste. And it looks like if I do the BOD test, 5D BOD came out to be same for both of them, 200 milligram per liter. Whereas ultimate BOD for this one is 457 and this one is only 243. So what is happening in here? This K value is higher, so that's why it's showing very quickly. And K value is not, higher here, that's so 5D BOD coming. But since the waste is not that strong, so it's flattening out very quickly. Even right after 10 days, it's flattened, right? Here it is even 20 days, it's to 20 days, even sometime 40 days to flatten out, right? So that's why it's very important to know the ultimate BOD. In this case, if I just know the 5D BOD, then I can say, oh, these guys are equal. Whereas these guys will take more resources to be treated compared to this one. So this is one of the scenario because the same 5D BOD but different, very, very different ultimate BOD. The other cases is, you see, I have a 5D BOD here for this waste, and the 5D BOD here. Here it is 50 and 21. So if I just use the 5D BOD, I would say this is very strong waste, right, compared to that. But it's not the case. If I continue that and ultimate BOD, I come up with the same. Okay, so what does it mean in this case? It means that like these two wastes are the same, but we could not say that based on the 5D BOD. We had to wait for ultimate BOD. So in here, you see the ultimate BOD came out to be what, 65 days around, 65 days. It's not 120 as I said. I said extreme value, but definitely it might take up to 120 days. So meaning that's the importance of BOD model, BOD equations, and to use those to calculate the ultimate BOD, although it may not be exactly the value that would be happening practically in the real life, but they are very close. If we are doing make a lot of mistake in calculating the value of K, then we are very close to the exact one. Precision, mainly precision is not that great, but it would be very close. Okay, now we'll go to dissolved oxygen sac curve. This is also known as DO-sac model or Streeter-Phelps equation. The concentration of dissolved oxygen in a river water is the indicator of the general health of the river water and also represent the capacity for self-purification. Whenever we say self-purification, what really it means? It means like say, if we do some kind of waste disposal in a certain part of the river or anywhere, the way it will take care of the waste assimilation and everything, it will not lose any kind of like say water quality standard. So that's the meaning of self-purification. Okay, one of the major tools of water quality management in rivers is the ability to assess the capability of stream to absorb waste. So that's the main idea. If we know certain river can absorb more waste, we can discharge it without treating, save money, right? Our ultimate goal is to save money. Save money means it's a business. Okay. Now, this is done by determining the profile of dissolved oxygen concentration downstream from a waste discharge. The profile is called the DO-sac curve. Okay, I'll show you some kind of typical profile. Because the DO concentration dips as oxygen demanding materials are oxidized and then rises again further downstream as the oxygen is replenished from the atmosphere. So it's saying a lot of things over here, right? So this is one of them. So this is a typical kind of curve. So this one typically is going that way. So because of the dip, we call it DO-sag curve, sagging in here. Now let me explain a few things here. In this curve, this line, dotted line, is a saturation level. Saturation level of the dissolved oxygen in water depends on the temperature. We'll see the tables and other things, relationship. And here is the one that we measured in there. So that means we measured and we got 6 milligram per liter, whereas due to the temperature it's supposed to be 9 milligram per liter. Okay, so what does it mean? Then the deficit is 9 minus 6 is equal to 3, right? So this is called the initial deficit. In this case would be 3.0 milligram per liter, right? Milligram per liter. Then when it dips, then this is the point. From here, this is the minimum amount of oxygen available, and from here to here, the maximum amount of, like say, deficit, that is shortage. So that's why this is called critical point. So this is the point will dictate us whether the river water will have good quality or maintain the quality of the standard, so that the aquatic life can survive. Then with time, more oxygen being added from the atmosphere and other part of it, then it's going up. So in this case, if I'm requiring 4 milligram per liter, looks like this part of the river water, this part of the river water is not good condition, right? So whatever the distance or amount time is. So more clearly, we can explain this one by this figure. This figure has a 5 zone, right? 1, 2, 3, 4, 5 zone. This is called the clear zone, clean zone. At this case, I see all the fishes and everything. In here, my BOD is very much kind of what? Close to zero. Maybe I don't have any BOD. Dissolved oxygen looks like in the higher level, whatever the level is. Then whenever we discharge this, then organic matter starting being used by the microorganism, then the oxygen is going down. Okay, so it went up to 2 ppm and went up. So BOD initially, like so this BOD was not high, then it came out to be kind of zero, right? BOD remaining. In this case, oxygen demand. We can say oxygen demand here. BOD remaining. So initially BOD remaining was very high, then it's going down, right? So you see this fishes clean zone. I see fishes. The decomposition zone, since it is dipping that way, this part still there are more oxygen. So I see some fish. I see some other things like say midge larva and other things. So this is only black fly can do it, right? Septic zone means very minimum amount of oxygen there. So sludge worms and midge mosquito larva can still be seen here, but no fish. And what is recovery zone, I can see whatever I can see here, big fish. And when it is clean zone means it is back up to almost what, 8 milligram per liter, 8 ppm, then everything is back. So in here, if it is 4 around here, I can say this area may not be good for like say fishing or anything like that. So we can use those for kind of like say warning and forecasting of to the people saying that there will be no fish around that area and so like that. So fishermen then they don't go there, try to fish, and whole day at the end of the day there is no fish. Okay. Okay, we can move forward. Now, in order to develop this model, TOSAC model, we use the mass balance approach. You guys are familiar with that. In topic 1, we discussed the mass balance. So, or as an engineer, we have to have a background of mass balance, how to do that. I don't know, in fluid mechanics, we do it, probably not that much, but here definitely it is. Mass of dissolved oxygen in wastewater that is coming into a system. So consider this is a system, okay, river or anything like that. Mass and dissolved oxygen into the river, whatever is in there, river coming and mix here. So this is the waste is coming here. And then after the mixing, the mass of dissolved oxygen in the river after mixing, so it's going out. So this has to be this plus this equal to this, right? So this is plus this equal to this. So that's how it is. Now we can calculate the amount of dissolved oxygen in the water. Dissolved oxygen to the wastewater can be calculated if I know milligram per liter, and if I know how much of flowing, how many liter is flowing per day or per things like per second. So I know this one is the dissolved mass of the dissolved oxygen in the wastewater. This would be in milligram per day or second or minute. Similarly, mass in the river, I can calculate whatever is coming dr and dor. So then if I add this two together, then I can make it a mixing. So whatever the mixing q, right? Mixing q, I think after the mix, and whatever the average dissolved oxygen after the mixing. Okay, so that means this plus this will be this. So that's our mass balance equation here. So we calculated more over here. So mass of dissolved in the river after mixing equal to the sum of the mass flows. So mass DO after mixing is this total, as I mentioned that. Okay, so the mass of BOD after mixing, like would be basically EWLW and other things like that. Dissolved oxygen, this is the BOD. So it could be done for both. Okay. Now, the concentration of dissolved oxygen BOD after mixing are representative masses per unit time divided by the total flow rate in here. So already I mentioned that. So here is the approach that we use in terms of the finding the dissolved oxygen and the L0 after the mixing. So this is Q is the flow rate of the waste, dissolved oxygen is the flow rate of the waste, QR is the river flow rate, DOR is the river dissolved oxygen. So if I do weight is QW and QR the weight, then we multiply those and divide it by the total. So you guys may be familiar with the weighted average, arithmetic average, right? In the all arithmetic average, we use 1 as a weight. So L0 similarly, like say QW, L0W, QR, L0R, QW, QR. So L0 is the ultimate BOD after mixing. So after mixing would be this. Now, if we have a temperature, two different temperature coming in and mixing, then we can calculate the mixed temperature is also the same equation. Okay, now let's try to solve this problem and see how we understand this. This problem is saying I have a stream A that is properties is flow is 3.7 meter cube per second, temperature is 21, and the dissolved oxygen is 4.5 milligram per liter. I have a stream B. There are characteristics are flow rate is 2.5, temperature 17, dissolved oxygen is 7.5. Now it's mixing in here and becoming a stream C. Now I have to find the value of the flow, temperature, and dissolved oxygen. So flow is very simple. We know continuity equation. Continuity equation equal to what? QA plus QB equal to QC, right? So it's very simple. From continuity equation, flow point at C, QC equal to this. It's very simple. Then combined temperature or the temperature at C, QATA, QBTB divided by QA, QB. So this is QA, this is QB, this is TA, this is TB, and this is the total. So I get 19.4. Similarly, dissolved oxygen at stream C. Okay, DA, T, QA, DOA, QB, DOA, and so on. Ultimately, I get 5.7. So I know my mixing temperature would be 19.4 and my mixing dissolved oxygen would be 5.71. It's very simple problem, right? So it's not a hard problem. Okay, now we'll calculate the oxygen deficit. Deficit means already I mentioned that when I showed the curve, I had a DOS, right? DOS is the saturation level can be. The other one is from the bottom, how much is available. The shortage would be this, okay? So in this case, we'll calculate this thing in here. So oxygen deficit rather than the dissolved oxygen concentration to make it easier to solve the integral equation that results from the mathematical description of the mass balance. Okay, the oxygen deficit is calculated as D equal to saturation level minus whatever the dissolved oxygen available. So this would be my DO, that is this available. This would be my D, and this would be my DOS. DOS is equal to D plus DO. So D would be equal to DOS minus DO. So that's what I have in here. The values of DOS for fresh water can be given in table 4.3. So in this case, here is the table. Okay, table 3. So in this case, what is showing here for 0 degrees Celsius, the saturation level could be up to this. For example 20, it could be 9.17. So with the temperature is going down, right? With 45 is only close to 6 milligram per liter. Okay, so that's how we know that the saturation level is there or not. So the deficit would be considered whatever is available and whatever is supposed to be. So that could be the deficit. Okay, this one I showed in different figure like that. This is in a kind of equation, polynomial equation. This is an exponential function. So both of them fitting very good, 99.4%. This is 99.99% even. This is even better fit than this. But you can use both. If you go more than 45 degree, then you should be able to use this equation to come up with the values of the, it can be extended like that. It can be extended like that, right? So as a trend, then you can get it from there too. Okay, so we are going to stop here for this one because then we'll start from the next slide.